The electron density is actually a very, very important concept that we use to explain certain things in organic chemistry, like the reactivity, the changes in reactivity. And as a definition of electron density, it's like, let's say, a representation of the probability of finding an electron in a specific location. But the electron density can move depending on the electronegativity, depending on what groups are attached to a certain molecule. And benzene is a perfect example to fully understand this concept of electron density, because we don't represent benzene as a molecule with 3 localized double bonds, but we represent it as a delocalized electron, so with this ring. To understand the reactivity, we need to think, well, there are 3 double bonds. So apart that those are delocalized electrons, it's also a region of high electron density, because a lot of electrons are centered there. So region of high electron density. If it has a high electron density, it means that it can donate electrons. So it would react with something more positive. And that's why benzene would react as a nucleophile. Nucleophile, as a definition, it's a electron pair donor. And it doesn't have a formal charge. There is no difference in electronegativity, but it has a region of high electron density. So we know that it will react as a nucleophile. Of course, the reactivity is lower compared to, as I said before, the localized double bonds, because those, they are able to induce a dipole. But this can't. So it's actually weaker than this, because the localized double bonds are able to induce a dipole, while benzene really can't. So it still reacts as a nucleophile, but we will need a catalyst to react with. And that's for another topic, like the formation of the catalyst and the reactivity. But we know that it reacts as a nucleophile, and it's important to really picture this concept of electron density and movement, because when benzene has substituents around it, the reactivity changes. For example, let's look at 3 of them. Chlorine, my benzene, they're all one different from another, but never mind. I mean, it's all approximation of the shapes. This is called toluene or methylbenzene, and phenol. Benzene react as a nucleophile. We got that because region of high electron density. But the substituent could change a little bit their activity depending on the nature of these substituents. Chlorine, it's more electronegative than carbon. And of course, it's really important to remember the concept of electronegativity, so the ability of an atom to attract electrons towards itself in a covalent bond. And again, is the movement at the end of this electron density due to difference in nuclear charge at the end. And chlorine, it's more electronegative, so it takes away the electron density from the ring. So this is called an electron withdrawing group. Withdrawing group. And it's very specific for these elements that have a higher electronegativity. So let's call it EWG, electron withdrawing group. Because it takes electron density towards itself, it would make the ring less negative. So if the ring is less negative, it's going to be a weaker nucleophile, because electron density is taken away from the ring. So electron withdrawing group, and here top of it, electron withdrawing group, they decrease the reactivity of benzene. It's going to be less reactive because it takes away, so because it has less electron density in the ring. Another type, so before looking at methylbenzene and phenol, another type of electron withdrawing groups are those that can take electrons towards itself, because that's at the end of the definition of electron withdrawing group, but any group that actually has a double bond that can take something on. So what I mean is, for example, a carbonyl or nitro group. Because when there is a pi bond, this pi bond can always move to the p orbital, so to make it negative. Yeah, so this could look something like this, where the electrons from the pi bond go onto the oxygen to give a negative charge. But what this means is that from the ring, the electron can flow, they can move towards that oxygen that can take that negative charge or can hold that negative charge. So those are two other examples of electron withdrawing group, those that have double bonds, because the electrons can be taken from the p orbitals of the other atoms attached, like oxygen, or more electronegative groups. Chlorine is, I would say, chlorine, fluorine could be the ones to know, even though there is a bit of a competition of this effect and the other effect that we will see for the other groups. But the ones to remember is nitro group, acyl, B-acyl, just addition of acyl group, or carboxylic acid like benzoic acid. Yeah, and then chlorine and halogens as all the halogens as electron withdrawing groups, so decrease their activity. The other two, so methyl benzene and phenol. Even though, yes, okay, oxygen is more electronegative, so we could say, yeah, but it has the same effect. Yes, but there is another effect that it's a lot more, let's say, important or better. It's more, it's stronger than the electronegativity, and this is called actually, it's called a resonance effect. But what it basically says is the opposite. Instead of taking the electron density away, it pushes it to the ring, simply because the ring has a higher electron density. So in the case of methyl, well, the electron density would be attracted to this more negative to make it even more dense. With the phenol, well, it has lone pairs. So those lone pairs can actually delocalize in the ring. And this delocalization would actually cause an increase in electron density. And if the electron density increasing, so will the reactivity. Those are two examples of what are called electron donating groups, because they donate electrons. So electron donating group. And of course, they do the opposite. They increase the reactivity because there are more electrons in the ring. Yeah, we always talk about this movement of electron density. Yeah, another example could be, well, anything else that has lone pairs. So amines could be a good example, because again, it has a lone pair that could be delocalized in this ring. So this rate is called a resonance effect. That's the name of it. They need to know the details why at this level, but this is called resonance effect, because the electrons delocalize in the ring, so they move around, so it forms what are resonance structures, which are basically structural molecules that exist at the same time. This is because the electrons can be in different positions at the same time. While the electron withdrawing group, this is called inductive effect. Yeah, written terrible. Inductive effect, which is this taking electron density, and it's normally felt through one bond. And this is normally inductive effect, normally due to difference in electronegativity. So this has a consequence on the reactivity. Electron withdrawing decrease it, electron donating increase the reactivity of benzene, which means that it has a consequence also on the uses of catalyst as well as further substitutions. But for now, let's take this in.